Thank you, Aigerim. We will take questions. Maybe before that, I can start by asking one question to you, Aigerim. So you were mentioning that you use deep neural networks. So maybe based on Shida's presentation, do you have any ideas about using state space models instead?
So actually, in Shida's work, we have also about SSM terms, but in his case, it's like state and space modeling, but in my case, it's speed and separation monitoring. So actually, I also, during your presentation, thought that is it be possible to implement your model in order to train my deep neural networks. However, in our work, we trained it using feed-forward neural networks, and we trained the robot in the real time. So there is actually no need to decrease the training time or testing time. So I think it is okay for me to keep in my side. And I want to ask the same question from Shida. How do you think your algorithm about state space modeling using laser activation function at the end of the hidden layers can be implemented in which kind of tasks?
Okay. Usually, state space models are used for the cases that you want to scale up the model, like you have a very complex task, and then a small model cannot do it good enough. But if you scale up multi-layer perceptrons or other classical models, then they usually have difficulty to implement efficiently. And the state space models is a kind of model that targets speed. Therefore, we can use state space models to model very large complex system without sacrificing the parallel degree. Then we can use GPU to accelerate this process. And they are more suitable for complex system, but for simple control system, then it might not be so useful.
I see. Okay, thank you.
Okay, please.
Hi, I've got a question for you, Aigerim. I wanted to ask how you solved your system in the turbulent systems. So, like, I'm from a background of low Reynolds number systems, where you solve it. You solve Navier-Stokes equation deterministically.
Okay, so actually we used.
Sorry, I got the wrong name. Yaswanth?
Yeah.
Sorry, I was sorry.
Oh, that was a question for me. Yeah.
Sorry.
Okay, could you please repeat it?
Yeah, sorry. I was asking about how you solve your Navier-Stokes equation in turbulent systems, because I'm from a low Reynolds number background where you solved a Navier-Stokes equation deterministically. So I'm just like, where does the noise come from?
Yeah, I get it. So the one that I have shown is very generic, simple. So I just considered, if you have observed, the divergence free. That is the only condition that I have considered. So I guess while using the full equation, the full Navier-Stokes equation, we'll have the issues with the time derivative, and that I have not considered, right? So I guess I have not explored it, I would say. This is just to illustrate that I think that's more complicated to get the restrictions. If you observe the f and g functions, those are the lateral and longitudinal components. To get the restrictions in such a way that they would satisfy the full Navier-Stokes, I guess it would need some more work. So I don't know if I answered that part of it. So, and once you get the restrictions, then we can talk about whether it is a low Reynolds number or a high Reynolds number, and then we can look into it. Okay. But for now, I'm not aware of any work which has obtained the restrictions in that manner. Yeah.
Thank you.
Sure. Yeah, please.
Hi, my question is also you, Mr. Yaswanth-Sai, Jetti.
Yeah.
So you explained that you characterize the randomness from naturally observed randomness and then incorporate them into the governing equations.
Right.
Could you explain a bit more about the process of incorporating that into the governing equation? So is there a conventional method of doing it, or does it vary with application and the governing equation?
Yes. So it's very specific to the phenomena that we are studying. So for example, I talked about the contact or the rough surface, which is most essential component to study any contact phenomena. So while doing that, we don't need to be really careful how we are incorporating the said randomness, right? We can just do a Monte Carlo simulation and get the get the contact results like contact stiffness, contact area, which are very important. But let's say we are talking about a conductivity phenomena in a microstructure which is random. The first thing that we need to do is figure out the so-called representative volume element, because that the randomness that appears or that comes out from the measurements, it need not be in line with the actual quantities, in the sense of, let's say, if you are talking about an elasticity problem, then you are talking about stiffness and compliance, and these are the quantities that are that might not be mathematically in line with the whatever randomness that is there. So we need to first do a homogenization type of a study and then obtain the effective properties which are corresponding to the randomness that is present, and then we can again maybe use Monte Carlo or maybe use some sort of stochastic finite element model to solve the problem. It's just the numerical method is just an efficient way of doing it, but I guess we can solve all these problems using Monte Carlo simulations, except that we need to be careful while looking at this particular phenomena needs some initial refinement so that we can further use the whatever numerical method we want to use. Yeah.
Okay, thank you.
Yes, please.
My question is also to you.
Okay.
I saw that you use your model to analyze surfaces.
Yeah.
But I saw that also part of your model is the fractal dimension.
Yes.
And I know from my research also that people use for the fractal dimension to analyze colloid aggregates or protein aggregates.
Okay.
My question is, have you used your model to analyze those types of systems?
I have not. I am I'm not very familiar with biological systems, I should be honest, but it would be very interesting. Maybe we can discuss after this. Okay. Yeah, because if you have any ideas, please let me know. I'm interested in, like I mentioned, I think these models can be are more general. It's just some randomness. I think they are present everywhere, and they can be applied to many phenomena, I guess.
Okay, we can speak later.
Yes, thank you.
Thank you.
Are there any other questions? Okay, maybe I ask Shida a question regarding your model. You said that state space models are better than the recurrent neural networks in the sense that the time complexity has reduced while we are using state space models. But you also mentioned that you proved this thing, that there is this memory effect, right? Did you think about any ways in which, are there any algorithms which still possess the advantages of the state space models, that is having less time complexity and also having no memory effects or memory issues?
Yes, actually, the state space models get popular because they are fast, but also because they can actually learn some long-term relationship. And this is interesting because you have a model that is having exponential decay in the asymptotic sense, but it can also learn some long-term memory for some horizon 0 to t. And this partially comes from the way that people parameterize the weights. They do not train a parameter directly, but they do some transform and then train it. And this will improve the stability of the algorithm compared with traditional nonlinear models. And actually, maybe a potential direction is to use the same method for traditional nonlinear models, and maybe it can also be improved in the long-term memory sense. Then we can still use the previous LSTM stuff.
I see. Okay. We still have 6 more minutes if you have any questions. Yes, we are. Yeah, thank you.
Thank you for all your talks. I'm Melanie, a PhD student in chemistry, so I have not really a relation to this topic, but I was interested in Aigerim's work for the Robotic when you said it's about the sudden interaction on fast scale for unexpected movements, but then I saw your video that looked more like a static movement around the human, so I was wondering, did you test or also more unexpected accident-related interactions?
Thank you for your question. Actually, we were training the robot using the dataset that I earlier mentioned, like ND dataset. So we trained the dataset, trained the model on that dataset. And during the testing, in order to make we cannot actually use the really different dataset from the trained models. So we actually used the same dataset, but actually, this dataset has like 13 different human motions, and the 10 of them we used for training, 2 of them for validation, and 1 for testing. And in order to test it for unseen situations, we just put the human close to the robot than in the training the data. So a human actually in the video is closer to the robot like for 10 centimeters than the actual than in the training dataset. So actually, that's how we test it for unseen situations.
Okay, thank you.
Okay, thank you everyone for paying attention to our talks.